All right, so yesterday we finished talking about acid halides. We said they're the most versatile carboxylic acid derivative. You can interconvert an acid halide to just about any other carboxylic acid derivative. The easiest way to make an acid halide is with dionyl chloride. We went through that mechanism. And this reaction is really favorable because we're forming that sulfur dioxide gas. One important thing to note is pyridine is often used as a solvent, especially if you want to soak up any of that acid byproduct that you're producing. So pyridine is commonly listed below the reaction arrow. All it is doing is acting as a proton sponge. The first thing we can do is interconvert this back to a carboxylic acid. That was super straightforward with water. We can also do alcoholysis, if that's a thing. Where if you take an acid halide, we'll do an acid chloride, and you react this with an alcohol, you typically run these with pyridine as a proton sponge, so I'll abbreviate that. You can interconvert this to an ester really easily, and then you end up with this pyridine salt. So it's a pyridinium chloride as your byproduct from this reaction. I'm not going to go through the full mechanism for this because it's really similar to that hydrolysis reaction. We also said you can do this with any sort of nitrogen-based nucleophile. And this works with regular ammonia, primary amines, or secondary amines. Whoops. However, this time I'm not going to use pyridine. Why do you think that's the case? Yeah, our nucleophile is also a good base, right? The alcohol isn't a good base, but in this case, the good workaround is just use excess ammonia. It can be both your base and your nucleophile for this reaction. It's pretty straightforward. And in this case, you would end up with an ammonium salt as your byproduct. Like I said, this will work with other amines as well. However, if you're going to use a primary amine, you still want to use it in an excess amount. And now you can go and form an amide. And last but not least, we can do this with secondary amines. However, these reactions are a little bit more sluggish because your nucleophile is fairly bulky. What's that?
Can you speed it up by adding heat?
Yeah, you can try to speed it up by adding heat. There's other techniques, though, for making amides that are a little bit more versatile, though. So you can do it this way. Typically, if you are going to do, especially this last one, you want to use a secondary amine that's not super duper bulky. So if you had two isopropyl groups coming off of your amine, you're going to have a hard time getting that to add in. All right. We can also do reduction of acid halides pretty easily. So let's talk about reducing these. It's not a super common reaction, but I suppose you could do it. What reagent do you think we would need if we want to go to a primary alcohol? PCC is the oxidant. LAH. So it's a carboxylic acid derivative, right? So we're probably going to use the same reducing conditions that we would use for a carboxylic acid, which is LAH in an excess amount followed by water. It's a pretty straightforward reaction. I'm not even going to show the mechanism, but treat it as H- as your nucleophile, right? So treat as H-. It's really just a hydride source acting as the nucleophile.
We use NaBH4 as well then?
No, in this case you want to use lithium aluminum hydride. That's a good question. I will show you guys an interesting problem though. So ideally, right, you're going to have this hydride floating around. I'll just show that as H-. It'll attack in, it'll kick up electrons. This will clamp back down, kick off our chloride. Some people will say, well, why don't we stop at the aldehyde? Why do we go all the way to the alcohol?
Because we have excess.
Yeah, we've got excess LAH. That's one immediate problem. The other thing, too, is we know that aldehydes are really good electrophiles. So this is a good electrophile. It is hard to stop here. But chemists are the type of people where they don't like being told they can't do something. So chemists decided, well, what if we really want to stop at the aldehyde? Does anybody have an idea? What's that? So maybe minimize the amount of reagent you're using? Okay, but even then they ran into problems where they would overshoot it. Don't use LAH. Okay, if we're not going to use LAH, what's a way to slow this reaction down?
Poison catalyst.
So poison it somehow. Another way we can maybe do this is make it so bulky that the reaction just slows down a lot, right? If you've got a really bulky reducing agent, it's going to have a harder time doing this transformation as quickly, and maybe we can trap it at the aldehyde. And that's exactly what happened. So let's make a note. What if we want to stop at the aldehyde? You got to get bulked up. Okay, so the bulked up reducing agent that was ultimately settled on as being the best is this guy. Give me a second to draw it. I think this reducing agent is overcompensating. It's got a lot of tert-butyl groups on there. So this is called lithium tri-tert-butoxy. Actually, there's a dash. Aluminum hydride.
Is there something short for that?
Yeah. Instead of writing this all out, people write LiAl. Sorry, let me get this closer together. OTBU 3H.
That's not like a short.
Unfortunately, this one doesn't have something like LAH. People will occasionally write it as LAH, but that gets confused with lithium aluminum hydride, the simple one.
Can you just write LaOH?
No. The one you'll see in the book, though, is LiAlOR 3H, which I suppose is a little bit easier, but the R is just a tert-butyl group. So either way, this is kind of a mouthful. It's a new reagent. The key thing is it's so bulky, it can deliver one hydride and then it stops, right? It doesn't have multiple hydrides to donate. It's a much, much slower reaction. It's easier to control, and it's a preferential reagent if you want to stop at the aldehyde.
What will that show up as on that ACS if it shows up?
It would probably show up as something like this on the ACS. I can't remember, though. All right, so let's take an example of why this is kind of neat. So I'm going to do this example. Actually, sorry, I'm going to change this to an ethyl group. So let's say we want to accomplish this transformation, where ultimately the only thing being changed is the carboxylic acid to the aldehyde. What do you guys think the first step would be? So we could protect the ketone, or what if we try to convert this to an acid halide? So for example, let's avoid the use of a protecting group for the ketone. What reagent would we need to turn that acid into an acid halide? Yeah, SOCl2. And then how can we go directly to the aldehyde? Our new alphabet soup reagent.
LOR3H.
The neat thing with this reagent is it won't reduce a ketone, or an aldehyde for that matter. It's too bulky. It will only reduce the acid halide. Yep.
Is the 3 supposed to be in the parentheses?
Oops, thank you. It should be outside. So the key thing to note is that it won't reduce aldehydes or ketones. It will only reduce acid halide. So it's a good workaround under certain circumstances. Does that make sense?
Not really. It looks like they're both equally accessible.
Well, if you think about it, right, an aldehyde is a pretty good electrophile, but it's not as good of electrophile as the acid halide.
That has a good reading to it.
So it really has to do with the electrophilicity. Acid chlorides are super duper good electrophiles, which means you need a relatively weak reducing agent. Aldehydes are a little bit less
Because you have
electrophilic.
oxygen and chlorine withdrawing electrons. Make it
Yeah,
electrophilic.
exactly. The chlorine, because it's electron withdrawing, it makes that carbon super duper electrophilic, which means a bulky catalyst can get away with reducing it. Okay, so let's take a look at another reaction that's a little bit different. Oops. And this involves organometallic reagents. So reaction with carbon-based nucleophiles. All right. Let's say we've got an acid halide, and I treat this with methyl magnesium bromide. What will our intermediate be?
The Cl swap for a methyl.
Yeah, so we're going to substitute the chlorine for methyl. I'm not going to draw the full reaction mechanism, but theoretically you could say, you know what? What if we stop at the ketone? Problem is we're running into a similar problem with the reduction. It's really, really, really hard to stop at the ketone. So instead, what this will do is react uncontrollably. And you'll end up getting a tertiary alcohol. So let's make a little note that it is hard to stop here. But again, a chemist isn't going to be satisfied with that answer. They'll say, well, what if I want to stop at the ketone? Is there any sort of workaround? And what do you guys think?
Yes.
Yeah. What might be an idea for slowing this down?
Bulky.
Yeah, use something that's bulky. In this case, we can't use a Grignard. We have to use an alternate reagent.
What if I want to do?
If you want to use a Grignard, you're not going to be very successful. But more power to you if you are cool with that. We're going to use something called a Gilman reagent, where it's R2CuLi. And this will stop at a ketone and won't add it in all the way to the alcohol. If you look at this organocuprate reagent or the Gilman reagent, it's a little bit weird you actually have two R groups covalently bound to copper, and that copper is coordinated with lithium. So this is an organocuprate or a Gilman reagent. And the Gilman reagent is very versatile. It's used in a lot of organic chemistry. We're going to cover it a little bit later when we get into, I think, chapter 22.
Do those R groups have to be the exact same?
Usually they are, yeah. All right, so this chapter's got a lot going on. Typically what I like to do at the end of every section is stop and make a mini reaction map. So that's what we're going to do now. We'll just do a mini reaction map only for acid halides. So in the center, I like to put my reagent of interest and then kind of fill out a map around it. So I'll do carboxylic acid over here. I'll do a ketone down here. I'll do a tertiary alcohol down here. I'll do an aldehyde. I'll do a primary alcohol. I'll do an amide. I'll do another amide. And another amide. And then last but not least, I'll do an ester. And then we need to figure out how to connect these. Yep. Yeah, let's just call these R primes so that we don't confuse them. Okay, so first one, how can we go from an acid halide to an ester?
Like some type of alcohol.
Yeah, some type of alcohol, and then we typically want a base. What's a good base? Yeah, so ROH and pyridine. The identity of this alcohol can be variable, so you can turn this into a wide variety of esters. Similar reaction for going to an amide. We said all you need is NH3 in excess, because in this case, it's acting as its own base. That's true for really all of these. So not too bad. All right. What about going straight to a primary alcohol? Yep, LAH in excess. Followed by a water quench. How do we stop at the aldehyde?
Sounds like a codon.
There we go. So our bulked up hydride source. How about our tertiary alcohol? Mm-hmm. And typically this is done with excess again, followed by a water workup. All right, and then with the ketone?
Copper.
Yeah, like Gilman reagent. So R2CuLi. And then what about going over to our carboxylic acid? Yeah, just water. That's no problem. So you can use water with the trace amount of acid. Alternatively, how can we go in the reverse direction? SOCl2, so thionyl chloride. I would argue this is the most important reaction map out of this chapter. If you understand this map, this will get you far. If you struggle with the amide one or the nitrile one, it's not a big deal because acid halides are the most versatile reagent. So that's the big takeaway from this. Does that make sense? You guys want to do a practice synthesis problem, or do you want to jump into new material? Synthesis. Wow, I never thought I'd hear that. All right, let's do a practice one. Oh, yeah. So let's try to figure out one to make. Let's do ibuprofen. So ibuprofen, most of you guys have probably taken this at some point in your life. It's a common anti-inflammatory drug. Let's propose a synthesis from benzene and carbon building blocks that are 4 carbons or fewer. It's going to be a little tricky. So I'll give you guys some time to work on this and then compare with your neighbor and see if you guys are getting close. All right, so when planning this synthesis, the first thing I would do is try to work backwards a little bit. Okay? So one thing I would say is we know a pretty clever way of installing carboxylic acids right now. So for example, let's say I have this as an intermediate. How can I make a carboxylic acid out of this intermediate?
Chromic acid.
Not chromic acid. We need to add in a carbon.
Oh, we do.
Right? So where did the carbon on that carbonyl come from? How could we add in one carbon? Grignard reagent. Okay, so in order to make this into a Grignard reagent, we'll toss in some magnesium, followed by what?
That's a great question.
Good question.
Wouldn't it just be an aldehyde? Or
Well, it has to be in the page.
So you could use something like formaldehyde and then re-oxidize it using a chromium-based reagent. I would prefer to not use a chromium-based reagent. What's another workaround?
It's formic acid.
I'll give you a hint. Think of bubbling stuff during Halloween.
Dry ice.
Dry ice, CO2. So if you remember, a Grignard reagent can attack CO2, form a carboxylate, and then step 3, we can protonate this with acid. It's a really nice workaround for making carboxylic acids. It's a lot greener than going through the hassle of oxidizing an alcohol. Okay, so now working backwards even one more step. How could we install that bromine? Yep, NBS. But then we kind of run into a bit of a problem, right? Why is this a problem? Oh yeah, we've got potentially a problem there. So now we've got to kind of come up with a workaround. So let's try to figure out a way around this. Does anybody have an idea? Ask Jeff. So let's maybe consider not doing the NBS step at this portion. What if we had this as our intermediate, right? That's an ortho-para-director. It's pretty bulked up. What reagent might we use?
That carbon with a Cl coming off bit with a ketone and a Cl at the end.
Okay.
I don't understand.
So you're saying treat this with something like this plus AlCl3?
Yeah, but then have a ketone so it doesn't rearrange.
Ah, so you caught the trick, right? You can't do a Friedel-Crafts alkylation directly with this because it will rearrange. We've got a primary alkyl halide. That would rearrange into a tert-butyl group. So a good workaround would be to do this first. So I'm going to slide these all over. That's why I like this problem, is it's a lot of review. Okay. Now, how do we get rid of that carbonyl group? Yeah, Clemmensen reduction. Oh. Okay. Now, if we look at this one, that's not too bad. Now we can do that MBS. And then how can we make this from benzene?
Ethyl chloride
Yeah.
and ASO3.
So ethyl chloride and aluminum trichloride. If you do run into the over-alkylation problem, you could use Friedel-Crafts acylation and then a Clemmensen reduction to reduce it if you are worried about that. So this is a good review problem, brushing up on chemistry from last term and then tagging on some new carboxylic acid chemistry.
Is that how they actually make it?
No. I would, if you're interested in how they actually make it, I'm pretty sure it's on Wikipedia, but this is a kind of roundabout way of making it.
Can I ask a question back?
Yeah.
How do you keep NBS from overbrominating that benzoic position?
So you have to only use one stoichiometric equivalent. Yeah. NBS in excess, you're absolutely right, would overbrominate. Okay, so let's continue on to anhydrides. Anhydrides are the second most reactive ones. They're used commonly as well. And the preparation is pretty straightforward. I said you can make anything from an acid halide. So what reagent would we need in order to make an anhydride? And I'll just call this an R prime over here. What do you guys think we would need? I mean, if you think about it, right, all we're doing is substituting this out for this.
Need a nucleophile?
Yeah, we need a carboxylate as a nucleophile. Okay. And that's exactly what's done. You get a carboxylate. I'm going to move this over. Actually, I'm just going to call this NaO. It's assumed to be ionic. And you can get this transformation to occur pretty readily. This is a really easy way. It can be used to make symmetric anhydrides, unsymmetric anhydrides. However, it's not used for the mass scale production of something like acetic anhydride. For really, really simple anhydrides, a different route is used. All you need to do for simple symmetric anhydrides is take a carboxylic acid, crank up the heat to a gentle 800 degrees Celsius,
Gentle.
and you can actually make an anhydride this way. Honestly, you'll never ever do this in a lab. This is only done for producing industrial quantities of anhydrides. The top route's way more common.
So does the top route not need any heat? Or
Yeah, the top route can be done at room temperature. So I'll just put this in the box because it is shown in the textbook, but for all intents and purposes, it's not very practical. Nobody wants to heat up a flask to 800 degrees Celsius. All right, so let's take a look at some useful properties. I think those of you that took 131 might have done this reaction. So let's say we've got this. This is salicylic acid. And all we want to do is convert this to an ester. And this is called acetyl salicylic acid. There's a couple ways you could go about doing this. One would be to react it with an acid halide, but what's the problem with that?
carboxylic acid.
Yeah, it might react with the carboxylic acid and give you an anhydride. Acid halides have a lot of power, and so they'll do reactions even with carboxylic acids. In this case, we don't want it to react with the carboxylic acid, so the best route is to use acetic anhydride, and you can actually install an ester where that alcohol used to be. Does anybody know the common name for acetyl salicylic acid? Aspirin. So let's make a note. This is more gentle than an acid halide. And will not react readily with the carboxylic acid.
We actually made aspirin.
Yep.
I think that's how we did it.
Yeah, in 131, I believe they give you salicylic acid, acetic anhydride, and then you have to check your product by melting point. It's a really popular lab for intro-level chemistry courses. You can also do a similar reaction.
They wouldn't let us keep it.
Where you can acylate nitrogens. And again, this is done with acetic anhydride. And now I've got a trickier question for you guys. My question is, why is it acylating the nitrogen and not the alcohol?
It's a better
Why is it the better nucleophile?
because we said so earlier.
Because we said so early. Because I trust you, Jeff, and I don't want to be wrong. This is tricky, right?
Because resonance.
If you think about the electronegativity, oxygen's more electronegative than a nitrogen. It's going to hold its lone pairs more tightly than the nitrogen. The nitrogen, because it's less electronegative, it's going to be more likely to participate as a nucleophile, which is why you get selective acylation at the nitrogen position. So really, this is just a competition showing that that's the better nucleophilic site. This is Tylenol. So acylations are very, very common for drug synthesis. Oftentimes they're cleavable groups where in your body will lop off the acyl group and turn it into an active drug. We're not going to spend much time talking about that, but if you go on in chemistry, you might talk about it more. I think there's actually a section in the textbook that goes and talks about it. Okay, so let's take a look at one other reaction of acid or anhydrides. And I'm just going to put a new in here. I'm going to try to skip over the redundant ones. So if you want a new reaction, let's say you've got an anhydride and you want to stop at an aldehyde. What do you think we should do? We can't use a really strong reducing agent or else it will go all the way to primary alcohols. What did we do for the acid chlorides?
We use the
ALO3.
Yeah, that one.
Yep, exactly.
If we write alphabet soup as our use thing.
I don't think that'll fit on your Scantron form for the ACS. Please don't put alphabet soup on there.
Actually, alphabet soup's a longer.
So again, this works with the bulky reagents. This will react with alcohols to give you esters. It will react with amines to give you amides, although it's a little sluggish. It will react with granurides. It will react with organocuprates. You can do a lot of these to interconvert them. However, this is kind of the newer one that we've covered today. So last but not least, before we leave, let's make a little bitty reaction map again for anhydrides. And I'm just going to do a generic amide. Up here, I'll do an ester over here. I'll do an aldehyde. Actually, let me slide this over here. We'll do an alcohol. So I'll do RROH. I'll do a ketone. See, we'll have our carboxylic acid over here to keep it consistent. And I think that's more or less it. We could add in the other amides, but let's try to keep it simple and concise, and then connect these together with arrows. Whoa. Okay, so how can we go from a carboxylic acid to an anhydride?
Add the carboxylate to the other one.
So we actually need the acid halide, right? Because we're starting with the acid over here. So that's one way to do it. Another way to do it is to do that super high temperature system, but for our purposes, we'll leave that out. And then if we want to go in the reverse direction, what do you think we can do?
It's not the Li.
So how can we rip apart an anhydride?
Isn't that the Li?
Not quite. It's really similar to an acid halide. How do we rip apart an acid halide?
Lots of water.
Yeah, lots of water, right? So this will react with water and convert it back. So these work well. One thing I will say is typically before you do the top reaction up here, you want to deprotonate it in order to turn your carboxylic acid into a better nucleophile. That makes it into the carboxylate salt that we needed. And then step 2 would be to react it with the acid halide. So that's pretty easy. All right, what do you guys think we should do if we want to go from our anhydride to a ketone?
RRCULI.
Yeah, the Gilman reagent, so the R2CuLi, because we know if we use a Grignard reagent, then we run into this problem over here. So I'll just call this R prime. So Grignard reagents add in uncontrollably, where the Gilman reagent will stop at the ketone. And then the other new reagent we just saw was the reduction to an aldehyde. Again, we have to use the super duper bulky reagent. So LiAlOR3H. Okay, and then if we want to go to an ester, what do you think we need? It's just like with the acid halide. Alcohol. So we'll call this ROH and pyridine. And then if we want to go to an amide, yeah, NH3, yeah. Or actually in this case, RNH2 excess. One thing I will note is that this reaction is slow. So we're kind of running into the limitation of some of these reactions. It's not nearly as fast as with an acid halide.
Would an R2 and H1 not work? Or?
No, you can use any amine. I just didn't want to draw all of them for sake of time.
Okay.
So what I would recommend doing is try to get a flashcard set up with these reaction maps and just familiarize yourself with all of these reagents, because it does become a lot to manage after a while. Tomorrow when we come in, we're going to switch gears and talk about esters, which are one notch down on the reactivity level.